Hey folks, today we're going to be talking about grasp planning, and this is the subject of Robotic Systems, Chapter 12.3.1. So when we want to do manipulation tasks, grasping is essentially the center point of the manipulation task. And so we have to think really carefully about how our gripper is going to be interacting with the objects that we want to actually manipulate. There are lots of different types of grasp planning algorithms out there. This is a subject that's still an active topic of research, and we can classify many of these grasp planners by either the gripper type that they work with or also the input data types that they work with. Now, the gripper types go in increasing order of complexity from suction grippers to parallel draw grippers up to multi-fingered grippers, which have a very high dimensional configuration space. And in terms of the input data, we can either think about looking at the geometry of the object that we want to examine and grasp, and try to figure out a way that we can geometrically figure out where we should grasp it. There are also types of grasp planners that deal with object poses. So they think in the kind of frame of an object itself and then use object pose recognition to figure out where that object is in the current scene. And then there's also image-based techniques that look at directly from the sensor data, try to figure out where to grasp. Now today we're going to be looking mostly at the geometric-based grasp planning, and we're going to be saving the learning-based grasp planning approaches to future lectures. But we're going to be talking about all different types of grippers as well as different types of input data. So when we build a grasp planner, we're going to be reasoning about a space of possible grasps. Now, to specify what a grasp means, we're going to say that a grasp tells the gripper where it should be, ignoring what the arm is going to be for the rest of the robot arm. So we can fully specify a grasp using a transform of the gripper base, as well as a configuration of the fingers, so that if I'm trying to grasp something, it tells me exactly where the gripper is in space, as well as where the gripper fingers are located. For certain types of objects, we may want to only partially specify, for example, the transform. In this case, for example, if we knew that we were trying to grab a mug, maybe we only care that we're trying to grab it around this axis, and we can grab anywhere along that axis. For multi-fingered grasps as well, we may also partially specify the finger configuration to let the fingers move. So if I want to pick up an object, for example, I could say, well, you need to have your fingers touching at this location, but I don't care exactly how your fingers are going to be configured. It's also very helpful when reasoning about grasps to include the expected contact points, the positions, normals, and friction coefficients, and also possibly semantic information such as what object you're grasping and what are its properties. In any case, the specification of a grasp in the most fully specified form is going to be a combination of SE3, so the pose, plus the configuration space of the fingers, which can be high dimensional in the case of multi-fingered hands. Now, one important thing to realize is that the grasp does not tell you whether it's going to be successful once it's actually executed. You could have grasps that penetrate through a table, or the grasp could be far away from the object, but we're talking about a grasp space, and elements from the grasp space will then need to evaluate them to predict whether or not executing them will be successful. So several different criteria make a good grasp. Well, first of all, we want to lift the object. Second of all, we want it to minimally shift the object's pose unless we expect it to. So if we're trying to, for example, pick up an object like this, a cup, and we misalign our fingers so that as we close our fingers, this thing gets pressed out of our fingers, that's not a good grasp. There's some unexpected movement there. We also, especially in clutter, want to not contact nearby objects if possible. If we're in a pile of objects where we could slightly touch the other objects and push them around, that's okay, but we don't want to jam our hands into the sides of, let's say, a container or the sides of a shelf. Also, we need to think about what's going to happen after I grasp the object, and so we want to be able to make sure that the object stays grasped during transfer. So if I want to move it from place to place, I don't want it to then slip out. The grasp also should be within the robot's reach, and also we should be able to carry out subsequent tasks with the object if we're trying to, for example, pour let's say, a bottle of wine, or if we want to hammer a nail. We want to be able to grab the object in a orientation and location that will allow us to do those subsequent tasks. So these different criteria are quite actually diverse. So some of these deal with the acquisition phase, what happens exactly when I grab the object. Others deal with the future operations that I might want to perform with the object. There's also different types of criteria that we need to think about. So these criteria 2, 3, and 5, and 6 think about the geometry of the situation. And these 1, 2, 4, 5, and 6 think about force-based criteria. So some of these combine both geometric reasoning but also force-based reasoning together. And then there's also the question of robustness. We oftentimes need to have grasps that deal with disturbances well. And so a couple of these deal with how those disturbances affect the grasp. So one type of grasp planner that we're going to be looking at that's quite versatile is the object-centric grasp database. The idea is that in a pre-computation phase, we can store grasps in an object's local frame. And these grasps will then online be used to derive world space grasps using an object pose recognizer. Basically, when we see the object that we've seen before, we'll then translate and rotate the grasps that we've pre-computed into the world space. Now, it just makes the job of the grasp planner, it boils it down just to checking whether those are reachable and whether they're collision-free gripping locations. The nice thing about this is that you can apply them to any different type of gripper. You can also use many different types of experience sources. So either you can have human teaching or human programming, just define which kinds of grasps you should use. You could also self-supervise by grabbing objects multiple times and just remembering the ones that actually worked. The nice thing about this is that also we can encode different criteria that are really hard to write down mathematically, such as whether this particular grasp is good to use this object as a tool. The downside of this approach is that you can only apply it to known objects. So for example, if you have an industrial robot, it's grabbing a certain thing and needs to pick it up. This is not such of a big deal. Also, if you had a warehouse that had a finite number of things that the robot had to manipulate, this is probably a reasonable approach. But when you're working with a very open world, like a house, for example, it's very hard to program in at the design time of the robot which objects that the robot will actually be interacting with. Nevertheless, this is still a very active type of field of research to use these types of grasp databases. And so, for example, the YCB dataset is a set of objects in the physical world as well as their virtual counterparts that we can use for this type of grasp database approach for manipulation planning. Now, if we don't know what kinds of objects we're going to be seeing, we have to resort either to learning-based approaches or geometry-based approaches, and we'll talk about geometry-based approaches this time. These approaches require you to know more about which type of gripper you're working with so that you can try to understand how the geometry and the forces of that gripper interact with the geometry and the forces of the object that you're working with. And these can be very simple, they can also be quite complex. Now for suction grippers, it's actually not so difficult. Basically, if we see a bunch of objects, or if we see an object, we want to find some location where the gripper can suck onto. And this basically boils down to the problem of looking for flat parts of the object. So essentially, we want to find a sufficiently large flat spot. We then want to orient the vacuum gripper so that it's oriented against that flat spot, and we just want to make sure that that orientation and position of the gripper doesn't collide with anything. It's also reachable by the robot. So here is an instance of a RGBD scene that a RGBD camera comes up with, and here these regions here are generated by region growing. They're sufficiently flat, but they're not necessarily all objects that we want to actually pick up. So it's not sufficient just to find flat spots, but we actually want to sort them in some way. So we want to be able to get rid of some of these things that are false positives. So for example, the sides of the bin or just empty space, which are flat, but they're not objects that we care about. There's also some false negatives that are also present here. For example, this crayon over here on the bottom left, as well as this tape roll in the middle. And so what we can do after using this kind of initial region growing method is we can then score different grasping locations to try to find ones that actually correspond with regions that are good to grasp. This is also known as a generate and score approach. The idea is that we'll sample a bunch of grasps, we'll then assign some sort of numerical score telling us what the quality is of this grasp, taking into account those grasp quality criteria that we talked about just a couple of slides ago, and then we'll pick the top locations to either execute or also go into some further processing, such as a manipulation planner downstream. Now, what goes into these scores? Well, for a suction gripper, there's a lot of different things that we need to take care of and think about. So for example, how flat is that region? If there's a region that's highly curved, we oftentimes don't want to grab it, such as this barbell, this pink barbell that's over here on the left side of this image. It's highly curved and probably hard to actually grasp. Also, this corner over here on of the bin, it's also curved and probably unlikely to yield nice suction between the suction cup and the surface. We also want to pick up vertical objects because we don't want to reach from the side of this bin. It may collide with other objects. It's also likely for the object to slip if it's being picked up from the side. And so we have a verticality condition that looks at the plane normal and tries to find ones that are pointing essentially upwards. Also, for objects that are quite long, such as this aluminum foil, if you pick it up on the side of it, the center of mass is going to cause a torque to be applied about your suction gripper, which is likely to pull it off of the suction cup. And so we want to measure the distance between the grasping point and the center of mass and penalize things that are too far away. Finally, if we can detect the material that objects are made of, then we can try to avoid trying to grasp porous objects like this cloth that's highlighted here in red. Now overall, I will combine these different scores together, and ideally, if I've chosen those weights carefully, I will be able to sort these different grasp locations and find ones that are actually favorable for successful grasping. Now, if I change my gripper, I have to change my scoring criteria. I also have to change my sampling criteria. So for parallel jaw grippers, it's a bit more complex because we have to not only pick the orientation and position of the gripper, but we also have to choose the width of the gripper. Now, what we're going to define is the notion of an antipodal grasp. Antipodal means that we're grabbing the object from two sides that are pointed against each other. And so we want to find points of the object whose normals are pointing outwards that can also fit within our parallel jaw gripper's width. We oftentimes also restrict ourselves to top-down grasping, which means that the gripper is always going to approach from the top-down orientation. We can also use this to reduce the number of variables that we have to think about in terms of the vertical position of the gripper. So we can, for example, just lower down the gripper until we hit the geometry or our fingers are surrounding some geometry. And so we can end up with a four-dimensional grasp space just by position, X and Y, the orientation of the grasp about the vertical axis, and the width of the finger. So in terms of scoring criteria, I want to think about the normality of the two fingers compared to the object's geometry. So I want to match the outward normals of the object's geometry with the closure direction of my fingers as much as possible. So the green location here is good grasp in terms of its normality. The red one is not. It's going to cause the object to turn as I close my fingers. I also want to look at fit. So if I have an object that's too wide, I definitely don't want to grasp it. I may want to reorient my gripper so that it actually fits around features of the object so that I can actually pick up. I'll also want to look at the finger clearance so that there's no objects around the target object that will interfere with my fingers. Essentially what I want to do, if I think about looking at the plane through my antipodal grasp, I want to look for a feature in terms of distance that looks like this. So distance is basically the negative of height. And so what I want to look for is a spike in the height with two pits of the height where I can fit my fingers into. So essentially a feature that looks like this on in the depth axis. And finally, I want to look at off-axis torque, just like in the suction gripper case. And again, I'll have a weighted sum of scores that will define the goodness of a grasp. The situation is much more complex for multi-fingered grasps. And so for geometric multi-finger grasp planning, this is a topic of active research. And there are three general approaches that are summarized in the chapter: approach and close, geometric primitive matching, and surface sampling. In a nutshell, the approach and close approach it tries to sample different approaching motions of the hand that move towards the object and then close the fingers, and then through collision detection you try to figure out the locations in which the fingers touch the object. Once we find those contact points, we can then score them and try to find good grasps by randomly sampling these different approach directions and finger configurations. Geometric primitive matching tries to identify common geometric primitives like boxes, cylinders, and spheres on the target object. And if I predefine certain types of grasping strategies, such as a power grasp to grasp around a cylinder, then I can come up with sampled grasps that grasp these primitives, and then I can also follow that up by collision checking and scoring to assess the quality of each of these grasps. Finally, surface sampling starts by picking contact points on the object, and then it tries to find a pose that will actually meet those contact points. It tries to make sure that the contact points that you've chosen yield a good grasp to begin with. Now, I won't go into much detail about these different types of approaches. You can read the chapter for more details, but I want to point out that the commonality between each of these approaches is that there needs to be some sort of method for assessing the grasp quality. It's not so simple as suction grasps or antipodal grasps because these contact points can happen anywhere on the object. They can be in any arbitrary orientation, and so we need to have more sophisticated ways of understanding whether or not a grasp is a good grasp. So as we've discussed last lecture, the wrench space is one great place to start. We can, for example, test to see whether the object is in force closure or form closure. The wrench space allows us to determine whether or not the grasp is in force closure. As you recall, the wrench space is a set of all wrenches that the grasp can exert on the object, and it's given by this expression here, where there's a matrix. This is a 6x3n matrix, where n is the number of contact points, and F here is the stacked vector of contact forces, each of which has to lie within its own friction cone. This is a block matrix notation here. Each of the first three entries, rows, these are going to be identity matrices, and then below them for the rows 4 through 6, these are going to be cross product matrices determined by the expression here on the right. Now, these are well and good for finding force closure, but we oftentimes want to not only determine whether we can resist a given wrench, but also how much force or how much effort we have to exert to actually resist that wrench. And for that type of purpose, we oftentimes use what's known as a bounded wrench space representation, which is very similar to the wrench space, except that we bound the normal force at each contact point to a maximum of 1 unit. Now, from this bounded wrench space, we can determine a lot of interesting things, but let's talk about first how to construct the bounded wrench space. So if you recall the friction cone, we can approximate it using a set of sampled rays along the boundary of the friction cone, and the convex hull of these rays will give us an approximation of that friction cone. This is known as the polyhedral friction cone approximation. Now, if I were to use a bounded friction cone, I can just take the convex hull of the unit force along each of these rays, as well as the origin, and that will give me a three-dimensional polyhedron that will tell me what each of my forces can actually do. And I can do a transformation to actually express the bounded wrench space as the convex hull of the zero wrench, as well as each of the wrenches that it results from a unit force along each of these contact point rays on the boundary of this friction cone approximation. So what does this look like? Here's some examples just in 2 dimensions. The workspace is going to be 2D and the wrench space is going to be 3D. And so you can see that for these 2-fingered grasps here, on the left hand, you see that grasping this long object from the sides gives me a slightly wider wrench space than grasping it from the top and the bottom. Also on the upper right, you can see that this grasp over here, which is kind of a weird grasp, it has one finger on the side, one finger on the bottom. This is not a force closure grasp. You can see that the wrench space does not have force closure either. You can see that on one side of the origin, there's just no way to resist any kind of disturbance wrench. And if you have 3 fingers, you have a much larger wrench space, and it can resist forces in a lot more diverse directions than any of these other 2-finger grasps. So in any case, given one of these wrench spaces, we can measure a bunch of aspects of the wrench space that tells us something about the quality of these grasps. I'll talk about just 3 of these very briefly. One of them is just going to be the wrench space volume, and that's pretty self-explanatory. Another is called the isometry of the wrench space. So the idea is that you want to have the wrench space be roughly as close to cylindrical or spherical as possible, so that you can resist wrenches in all sorts of different directions. And the way that this is defined is the ratio of the maximum inner sphere centered at the origin that can fit inside of this of the wrench space, divided by the radius of the smallest outer sphere that bounds the size of the wrench space. Now, this is a reasonable approach, but we can also look at just looking at the inner sphere itself as a metric, and this is known as the Q1 metric, and these are illustrated here. A final step in grasp planning is verifying whether the robot arm can actually reach the intended grasp. There's a couple of ways to do this, and one of the first steps that you typically need to do is just to figure out whether or not that grasp location is actually reachable. And we can use a structure called a reachable workspace to determine whether or not there's any chance of the robot arm actually grasping the object from that location. The reachable workspace is a set of locations that can be reached by the robot's end effector. This is pre-computed in the absence of obstacles, either through geometric methods as shown on the left or through sampling as shown on the right. Now, this is a pretty good, at least first attempt at verifying reachability, but it's not perfect because the reachable workspace is also affected by the orientation of the gripper, and it's also affected by environmental obstacles. So for example, if you're trying to reach into a shelf, you have to really think carefully about whether your arm actually collides with a shelf or the shelf doors and other kinds of obstacles. So to do a more precise job of verifying reachability, we have to use a process called inverse kinematics. The idea is that we're trying to find a set of joint angles that meets a certain Cartesian position and or orientation. Now, whether we're trying to reach position or orientation or some subset of those constraints is known as the task space of this inverse kinematics problem. They describe which dimensions of SE3 are we trying to actually reach with the robot's end effector. So this can be the full SE3 constraint of a fully specified grasp, which is also known as a fixed task. We have both the position and the orientation fixed. You could also have, for example, hinge constraints, such as for antipodal grasps, we only care about the center and the rotational axis of the closing axis of that grasp to be matched. And there's also other types of inverse kinematics task spaces that we can try to define for different types of grasps. So for example, for grabbing a ball, we only need to constrain the position of some point in the center of our gripper. In any case, we'll talk much more about this in the next lecture. So in summary, we talked about grasps and grasp spaces. The grasp spaces consist of the gripper-based transform plus the finger configuration. And what's important to note is that the grasp space doesn't tell you whether the grasp is actually going to be successful or not. That's the job of the planner and also the scoring algorithm. We talked about grasp databases, which are very versatile, and they pre-compute these good grasps offline and then reuse them by transforming the grasp to wherever the object is located in space. We also looked at geometric methods that can reason without predefined object models, and these typically use generate and score approaches, which sample some set of grasps and then try to assess the quality of those grasps. Next time, we're going to be talking much more about reachability determination and using workspaces and inverse kinematics, and hopefully put together much more of this manipulation pipeline. See you next time.